Welcome back, class. We will continue the second part of this chapter, chapter 6, BJTs, and we are still in week 9. So with this recording and the next one, I will hope to finish chapter 6. So this recording will do the lecture part, the theory part, and the next one I'll look at a few problems. Again, this is the second half of what we plan to cover. This is not the whole of chapter 6. Like I've said before, in chapter 6, in this edition, 6th edition of the textbook, I'm only planning to cover 1 to 5. 6 to 9 will be in your next class, next EE 380 class next year. For now, the plan was to do the first 5 sections. We've already done 1, 2, 3. Both the theory and the problems were completed in the last recordings. So for now, the plan is to do sections 4, which is the applying the BJT in amplifier design, and section 5, small signal operations and models. Okay, so to get to section 4, I have to skip many slides in my PowerPoint. I will skip to slide 39. Yes, okay. So I'm on slide 39 of the PowerPoint, and as you can see, this section 6.4 BJT amplifier design has a number of further subsections: 6.4.1, 2, 3, 4, 5, 6. So lots of material to cover. And then we have one more major section, 6.5, small signal details. So the two of these in the next 45 minutes is what I intend to cover. So moving on to slide 40, here we are introduced to the idea of the voltage amplifier. Okay, now we have done op amps and all that, so I don't think amplifiers are too new to you, but nevertheless, for purposes of applying a BJT into amplification and for amplifier design, there are a number of steps that we need to understand, and so that's what we are going to go through in the next few slides. So why do we have to understand the BJT as a voltage amplifier and not just any amplifier? Well, we've already been introduced to this formula on the top left, right, where we are saying that the current IC, which is the current in the collector circuit, is proportional to this VBE, which is in the base circuit. So we have already made the statement that the collector current, if you think of it as an output, is dependent on a base voltage, which is the VBE, which is an input. And the other factors in this formula are constants anyway. But connecting an input of a voltage to an output of a current is useful, no doubt. But what is more useful is if you can connect the output voltage to an input voltage. Then it makes the job easier, right? Then you can define a simple amplifier gain as just V out by V in. So we can get that V out by V in by not just looking at the current, the collector current, as the output, but by looking at this VO, which is the VCE, as the output, right? Once you do that, then you have an input voltage VBE and an output voltage VCE, and the ratio of that will give you the gain. Now, how do we get the VCE? We have to use the KVL on this circuit, and so simply put, the VCE, or the output, is nothing but VCC minus the IR drop in this resistance, the collector resistance, and then you can actually rewrite this formula, the KVL, to say VCE equals VCC minus, this factor, where instead of IC you put this in. So you put all this in, now you have a formula for the output, the independent variable or dependent variable as equal to something into the input VBE. So input VBE is amplified to output VCE, and thus we have defined a voltage amplifier. Okay. So that was slide 40. I'm going to move on to slide 41, and here we are introduced to a graph called the VTC, or the voltage transfer characteristic. This is pretty neat because the output is on the y-axis and the input voltage is on the x-axis. So you have a straight relationship between the input and the output, right? And you can see that there's a bit of an exponential curve here, and then you have these areas called the active and the cutoff and the saturation that you have already been exposed to. So what this says is, the graph says that there is a cutoff section where the output voltage is very high and the input is low up to a certain point, 0 to 0.5 volts, and then there is almost a straight section, but it's actually an exponential fall, which is the active mode, and then you enter saturation. Okay, so this voltage transfer characteristic is what is generally used to help us define the operation of a amplifier, of a voltage amplifier. Okay, so I'm going to move to the next slide, 42, and here we are introduced to one more concept called the Q point or the quiescent point. Also, it's called the operating point. Okay, so we see the VTC from the previous slide is shown here, and we see a point Q has been picked in the middle of this active region, and that Q has two coordinates, the x coordinate and the y coordinate. The x coordinate corresponds to the VBE, the input, and the y coordinate is the VCE, which is the output. Okay, so this is a way to visualize the operation of the amplifier. Moving on to slide 43, now you can start to see the introduction of some signals. So far we just had a Q point, which is at one point with a certain voltage on the input, certain voltage on the output. You're just sitting there, right? The transistor is not doing much. But now we slowly bring in a small VBE, and that is a small disturbance or a small signal that is introduced into the base emitter circuit. And from the drawing to the right side, you see that if the signal is shown here as on disturbing the x-axis, right, around the Q point, a certain value of the signal, a small signal, is going out around the Q point, then a much bigger output voltage is seen around the VCE, around the Q point on the y-axis, which means the VCE is shifting up and down. Okay, so this shift, this relationship between the input and the output, or the output and the input, is what is interesting, and that is where we start to define the small signal operation and the small signal gain and so on. Okay, so basically I hope you understand that first we define a certain operating point by picking a certain VBE and a certain VCE, and then we introduced a small disturbance or a signal voltage, a signal riding on the base circuit, and that gives you a change, a much bigger change hopefully, on the output, which is the VCE. Okay. So what is this voltage gain, right? How do we define it? We can do a lot of calculations, which the textbook does, and please go through it. As I always say, I will give you the summary of the important formulas, but to understand more and how this is derived, you will have to read the textbook. But here is a definition of something called a gain, a small signal voltage gain. And what is the gain? AV, it's the output voltage by, it turns out to be all of these factors. The IC is the current in the collector circuit, RC is a fixed resistor, VT is the thermal voltage, you know what that is, it's always fixed. So you can reduce this to VRC, where VRC is the voltage across the collector resistance, and so the AV is kind of fixed. The gain, the voltage gain, AV is a fixed quantity, but it does depend on the biasing current, IC. Okay, so remember that fact. So I've got a few bullets here to explain what exactly we just did. To maximize the voltage gain, we should use as large a voltage drop across RC as possible, right? The more the voltage drop here, the more the numerator and the more your voltage gain. But the problem is you can't keep increasing RC as much as possible. Why? Because to increase VRC, we have to operate at a lower VC, right? As you increase this, this decreases. A lower VCE means a bias point closer to the end of the active region. That means you're starting to go into saturation region. So there is a limit on how high RC can be. Assuming you have a fixed VCC, you can only go so high on the RC without running into saturation problems. Also note that the AV has a negative sign, so what that means is the input is inverted when it comes to the output. Okay, so these are some properties of the gain, and I am moving ahead to slide 45. So we have some problems, and I am not going to do the problems now. I'll wait to do the problems in the next recording so that all the problems are together and we don't miss the flow of the theory. Okay, but in the problem I'll tell you that what we'll try to do is to use the definition of the gain that we just used or just created, and if there is a small signal V1, which is a microphone, a 1 millivolt signal, then if the microphone is generating a small signal, then what will be the output voltage, output signal, right? So we know that a microphone has to be amplified and you want the music to be heard on a speaker, but to drive a speaker you need a higher voltage. So basically this is like an audio circuit that takes a small signal on the microphone side and gives you a high signal on the speaker side. But we'll hold off on how to do this until the next recording. Okay, there's also an example in the textbook, 613, a pretty nice example. It also deals with all of these questions about how to pick the bias point, find the voltage gain, and so on, but we'll wait to do it in the next recording. Okay, so moving on, how do we create that VTC, right? The voltage transfer curve gives us a lot of information, but to be, and let me just show you that one more time so that the voltage transfer characteristic, right? This is important because right in the middle is where we find the Q point, and then we create the amplifier. But to create this VTC you need some data, and so what we are being told in the slide 47 is that there is a way to create the VTC. And to create the VTC, we have to plot the load line. I know we've been introduced to the load line previously. I think when we were doing diodes also I talked to you about the load line. the load line just is the straight line voltage characteristic across this collector resistor. Okay, so if you did a KVL around this circuit, uh, that KVL will give you the load line, which is a straight line, so it has to be in this form y equals mx plus c. So I show you the steps here, but basically this is a line with a slope of minus 1 by RC. Okay, now if you take that and you plot it on these curves, I know we have talked about these curves before. For every base emitter voltage VBE, we know a certain collector current comes up, right? And so for a number at different V base emitter voltages, you're going to have different curves like this, right? As you increase the base emitter voltage, this base emitter voltage, the biasing voltage, you'll get higher and higher values of the collector current. Okay, so that relationship and the combination of the load line together helps you pick a number of points. So for example, this point, right, this is where a VBE line intersects the Q point. Similarly, this point, this point, this point. So right here we see 4 points, and maybe this lower one 5 points, that give you a certain combination of V of this VCE and this IC. Okay, so you can take these values and then transfer them, going back to the VTC. You can put this VBE and VCE combinations and thus plot that other curve. Okay, so that's what this is supposed to do. So this IC VCE graph helps to locate the Q, which is, you want to always locate it somewhere in the middle, so you get the benefit there. Also, the VTC can be determined point by point from this graph. So valid IC VBE points, so valid points are picked from this graph to create the VTC. Okay, so we are not doing this too much manually in this class or in the exams, but you need to know that this is how amplifier design can be done. I have an example here. Again, I don't want to, there's 2 slides here. I don't want to scare you to think that we're going to do analysis of this type. This kind of analysis is what you'll do actually in your next course, EE380. This is an example of a common emitter amplifier, but I wanted to show you that to be able to completely analyze an amplifier circuit, there are a lot of little details. We are going to study a few details and get some idea, but the full analysis is beyond our scope. But nevertheless, you can take a look at this circuit, see how all of the various parameters, IC, IB, IE, and then these biasing currents. This biasing network actually, using a voltage divider method with 2 resistors, is a very specific biasing method that you will study later on. There's actually a number of biasing techniques, and all of this, luckily for me, I don't need to cover. All we do in my class is we pick one resistor, and that kind of gives you biasing, right? But in a real amplifier circuit, you do this. Another part of the same problem that I wanted to show you, again, don't worry, we don't have to actually learn how to do all this yet, but what you'll notice here is in this example, there is a load line, and this is a 1.2 k ohm collector resistance that I told you. So you plot that. All these blue lines, you get that from the manufacturer of the transistor. So the transistor manufacturer will give you this drawing, or you can download it from the data sheet, and then you put your load line on it, and then you say, okay, right in the middle I'm going to pick my Q point, which corresponds to about 46 microamps, and then my base circuit current can go like that, right? And my output voltage VCE comes out. So this is the input. On this side you have one output, which is the collector current, and then on this side you have another output, which is the VCE or V out, right? So all the data related to this amplifier circuit is all in one drawing, and I thought I'd just show you, how all this comes together. We don't do to this level of detail in this class, but once you finish the next class, all this will become pretty easy for you, okay? But we will learn a few steps that will help us to finally do the full circuit analysis. So what are these small steps? Let's keep going and you'll see what they are. Okay, so the next section, so that section was 6.4, and I covered a basic introduction to the Q point, the VTC, and I introduced the fact that you first create a Q point, which is an operating point, and then you slowly introduce a small signal that will swing the input value, the base current or the base voltage, slightly around the Q point, and then because the circuit the transistor circuit behaves as a natural amplifier, then that small swing around the Q point on the input side becomes a bigger swing on the output side. Okay, so we are going to study just a little more of the details behind how all that happens. Okay, now as you can see, 6.5 has a number of subsections, 6.5, 1, 2, 3, all the way to 12. So let's get started to see what are these what are the primary details here. Okay, so small signal analysis by superposition. I think you pretty well know what superposition is, even from our very basic material we learned way back in EE 188, right? We were doing basic circuit analysis and we studied superposition. Superposition means if you have two different sources, voltage sources or current sources in a circuit, you can analyze them one at a time. So you kill one source, look at the impact of the other source, look at the voltages and currents, keep them. Then you kill the second source, activate the first source, again look at what currents and voltages come out, and then you add them and you get the sum, the total effect. So that superposition business, we were told, only applies to linear circuits, right? So we saw this in the case of a diode also. We have a diode characteristic, the diode current and the diode voltage are related to each other, not really through a straight line relationship, not really linear, but through an exponential. But we said if the variation, the region that we are working in is small, then we can pretend that it's linear, right? That's how we were able to proceed and create some formulas for the diode case. And the formulas were pretty nice because they always come out to be A plus B. If A is the result of one voltage source and then B is the result of the second voltage source, if you add them, it works out fine. But that only applies if you're operating in the linear region, and we saw that with the diode, and I'm telling you it's the same theory with the transistor also. As long as, because again the transistor relationships are all derived from the diode relationships, right? So as long as you stay with small variations around the Q point, then you can create formulas that are simple addition, and then it reminds you of superposition. Okay, so you have an actual amplifier it has the bias voltage, the big VBE, and the signal, which is the small VBE, right? And all this is in one circuit. So what you can do is pretend that first that this doesn't exist, the small signal doesn't exist, and we are only calculating using the big signal, the biasing signal. Then we only look at we take out the biasing voltage and only have the small signal voltage, and then we derive some more currents and voltages. And then we say, okay, add them all together and we have the total uh, um, output. Okay, so how do we do this is the next few slides. Again, much of the derivation of how the small signal formulas, the linear approximation formulas are derived is in the text. I'm not looking at them in too much detail. I'll just give you the final results. So, small signal approximation. Assuming that small signal is less than about 10 millivolts in a typical transistor, you can say that the output current, for example, the collector current, is in this form, okay, and it is clearly the sum of a biasing current IC plus another factor. Now this factor is because of the VBE, the signal voltage, okay, and so if you can come up with this straight arithmetic where everything is a constant and just that small signal is all you have to put here, then you actually again kind of recreated or use the principle of superposition, right? So what is this small thing? We call that IC. So big IC, small IC. This whole thing, if it is equated to small IC, then within this there is another factor called transconductance. This capital IC, which is the biasing current divided by the V thermal, is defined as transconductance, and it has this value Gm. Once we have Gm, we can say that small signal portion of the total collector output, the collector current output, is the small signal component is this Gm times VBE. So we are actually connecting the voltage, the input voltage signal, to the output current signal through this factor called transconductance, right? So once you define it this way, it's a current, right? Conductance is obviously the opposite of resistance, right? V by R would be resistance, or V by I would be resistance, I by V would be conductance. So this transconductance, it's giving us a way to take the input signal, which is a voltage signal, and come up with an output signal, which is the current signal. So what is the transconductance? Here's a little drawing that tells you that it's the signal riding on the base emitter voltage. As it goes up like this, the output, which we are still considering the current, right? This current IC. We are not yet converted that to the voltage, which we'll do in the next step. But you have to understand the definition of transconductance, and that's why we are stopping on this slide 52. Okay. Let's move on to slide 53. I promise you we'll come to the voltage amplifier definition in a second, but we have a couple more things that we have to learn related to the small signal. Now all this is related to the small signal, okay? Don't forget about the biasing signals for the moment. So what are these two new parameters? There is something called the small signal input resistance between the base and the emitter, and it's generally shown as R pi, and it's defined as R pi is VBE, which is the small signal in voltage, divided by the small signal current. So that gives you, this is V by I, right, is resistance. And so looking into this circuit, between the base and the emitter for an NPN, you define the R pi as VBE by IB. It also happens that this R pi is related to the beta of the transistor, which you already know, and the GM, the transconductance, which we just defined in the previous slide. It also equals this, Vt, V thermal divided by I base. So all of these parameters, they're all interrelated, right? And here's one more definition, beta plus 1 times Re. What is Re? Look at to the right side. If you're looking at the base emitter circuit from here, from the bottom, then Re equals the base emitter voltage, the same voltage on the numerator here, base emitter voltage, divided by the IE. So assuming this IE current also exists, then Re is defined in this way, okay? So Re also is related to other transistor parameters like the alpha, the GM. Alpha is generally equal to 1, so it's approximated. It's equated here, and then R pi and Re are related. So all these different resistances, transconductances, etc., are all supposed to help us to create a small signal model that helps us analyze the small signal implications or the small signal effects in a very algebraic way without having to worry about the exponential behavior of the transistor. Okay, so by first of all defining the small signal to be of a certain value, roughly 10 millivolts, we are then saying that the analysis, now we know to analyze the Q point, we already only use algebra, right? That's easy with all the capital values. But similarly, to analyze and come up with the small signal values, also we can use algebraic methods, but we will rely on these three new factors that were defined. We define the transconductance GM, we define this input resistance R pi, and we define this emitter resistance Re. So using these three, plus of course the alpha, the beta, the Vt, thermal voltage, all these will help us to solve problems that are asking us to analyze the small signal effects of a transistor amplifier. Okay, that's why we have to study these. Now how these are derived, again they are in the textbook. Please take a minute, but to solve problems you need to understand what I am showing you here. Okay, now moving on to slide 54, we finally come up with the definition of voltage gain. And why is voltage gain important? Because we said that the easiest thing to understand about an amplifier is the ratio of the output voltage to the input voltage, right? If you give me that definition, then I can easily talk about amplification all day long. And so to help us do that, we have this definition. The most important definition, of course, is AV is the output small VCE divided by the input small VBE, meaning the signal only voltages, right? And what is this? How can you guess? Can I just look at a transistor circuit and say, yep, I can guess what the amplifier gain will be? Yes, if you can calculate GM, which is not too difficult because all it needs is the collector current, because V thermal we generally know, so GM is not difficult to calculate. So even without actually going into the small signal analysis, it doesn't matter whether the small signal is a 1 milliamp current or a 1 millivolt microphone voltage or a 1 millivolt signal coming from some kind of sensor or it's a 5 millivolt signal coming from a radio circuit, it doesn't matter. As long as you have a transistor amplifier and you can at least calculate the GM very quickly based on the Q point current IC, you can say, yes, whatever signal you put into the base circuit, I can roughly tell you what the output signal will be because the gain is this simple relationship. Okay, so that's the benefit of knowing the voltage gain. Okay, so that's slide 54. I will move on to slide 55. Here's a little more theory that we do need to understand. So nothing new. I think by now this material is familiar, but I wanted to emphasize something important here, and that the fact is that in any amplifier circuit, okay, now this circuit on the right side is not a real circuit. Why? Because it's missing the biasing details, right? So if you just had this circuit with maybe a 1 or 2 millivolt signal generator here and nothing else, the circuit will never work, right? Because we need biasing voltages at least greater than 0.7 volts to have these diodes conduct. So this circuit is just a symbolic circuit. It is only showing you the small signal relationships. But the reason we show this is to make our job easier of analyzing, right? So on the left side, I've got something that I want to tell you, and then the right side. The left side, I'm saying every current and voltage in the amplifier circuit is composed of two components, a DC component and a signal component, right? So for example, looking at just the base circuit, VBE, and see how it is written, there is a small v and a capital BE, is the sum of a big V, capital BE, plus a small v, BE. Why do we write it like this? We write it to make the point that if you look at this voltage here, VBE, right, this voltage, it will be the sum of, well, actually don't look here, maybe I should take you to another circuit. Give me a second. Yeah, if you look at this, maybe I should, well, okay. If you look at the actual amplifier circuit and you see this V with the capital BE, that is the sum of this VBE plus this little VBE. Okay, that is what we are trying to say on this slide 55. So at any point in the circuit, you will have the DC component plus the signal component. Same thing with the current, right? We show this as the I with a capital C equals a capital IC because of the biasing plus the small I small c because of the signal. Okay, so that's what's on the left side. On the right side, basically all I've done is put together all the formulas for the small signal that we have just so far learned. The small signal gain is in the middle here. The GM, the R pi, the RE, and then how are the currents and the various currents related to these factors? They're also here. Okay, so all this is in one place, and you might need to refer to this when we are doing problems. Okay, so the next slide 56, is a problem where we would be using the information from the previous circuit, previous slide, to find all these instantaneous values, but I will wait to do this in my next recording, and we'll jump to slide 57, where we introduce the idea of the models, right? In this textbook and many textbooks, these models are are given a lot of importance, although the writer also says, hey, the models are there, use them to learn the subject, and then once you know enough, you should actually not have to look at the models. You should be able to directly solve them on the circuit itself. Okay, so he tells us both. That's why I don't think the models are too important, but at the same time you need to know what they are and why they exist. So in this model, the transistor amplifier is shown to be a voltage controlled current source, also called a transconductance amplifier. And here the model just says, on this side, show me just the R pi, the input resistance, looking into the base emitter circuit. And then the right side of the model, you use the transconductance, and the value of this output, the collector current, can be just written by the simple formula, which gives you the dependent source, right? Dependent current source. So the model is that the dependent current source can be shown to be dependent on an independent voltage source VBE by multiplied by this factor GM. And to find, but you also need to know R pi to complete the model. Okay, same thing here, but here instead of a GM, he is using a beta, but it's still beta times IB, the base current here, instead of directly using the base voltage. Okay, so it's still a current controlled current source. Okay, or you can call this a current amplifier. Here we call it a transconductance amplifier. Okay, there's another pair of models called the T model, and here again we talk about a voltage controlled current source, but instead of showing the R pi, we show the RE, the other resistance, which is the resistance looking from the emitter circuit. Okay, so this model also is useful. So as we do problems with the models, you'll get a better feel for why they are important and why they are useful. Okay, the basic benefit is, once you establish this model and these relationships, which are just arithmetic, right, and multiplication, then if they give you different signal values, then you can very easily plug those values in and come up with the values for the output, either the collector current or the voltage, the output voltage. Okay, so the T model also exists, and the hybrid pi model exists, and we'll see how they are used when we do some problems. Okay, so a couple other quick things to do, and I'm trying to finish this in 50 minutes, so let me quickly go through it. We have to learn a little more about the PNP, right? So far everything we have done is with the NPN, but really nothing changes with the PNP except that you know that once we talk about PNP, the biasing is different, right? With the NPN, the forward junction, the forward biased emitter base junction, and the reverse biased collector base junction, right? Same thing, but here with the PNP, you still need the forward bias and the reverse bias, but obviously the sign of the batteries have to switch. So does anything differ? No, you still have no change in polarities. All the formulas we have learned still apply, and here was I found another quick guide to how to understand whether a PNP is in saturation or inactive. Look through this, and this may help you also to understand active, saturation, and cutoff. Okay, so I have a problem that we look at for PNP when we do problems, and we come to kind of a summary of how to go about applying everything we learned into a 5-step process to solve a problem with a small signal equivalent model. So let me quickly read each step. One, eliminate the signal source and determine the DC operating point. So generally you will be given a circuit, it will have a DC source for the biasing and a signal for the signal analysis. So step 1 is to take out the signal source and just pretend that there is only the DC source, find the operating point or the Q point in terms of the DC collector current IC and the VBE, applied base emitter voltage. Calculate the values of the small signal parameters GM, RPi, RE. To do all this, you don't need anything to do with the small signal yet. Once you have step 1, you can do step 2. Okay. Then step 3 is where you take out the DC biasing voltages. Now with a short circuit for a voltage source and an open circuit for a current source, remember? So take that out and you're left with just the small signal circuit. Now replace the BJT with one of its small signal equivalent circuit models. So either the pi model or the T model, put that in, and then the last step becomes easy. You can analyze the resulting circuit to determine the required quantities, voltage gain, input resistance, etc. Okay. So there is an example. We will do this, and that will explain how to actually use that 5-step process. I will come back to this. There is also a problem from the back that I will do in the next recording. Here is the point about the direct analysis. So the writer says in the textbook, hey, I taught you about the models, the pi model and the T model. It's great, you should know that. But more important, you just should be able to just apply those ideas directly to the given circuit without actually drawing those models. As long as you understand the concept and you know the relationships, you can go through this 5-step process: 1, 2, 3, 4, 5. Okay, and we'll do an example also using the direct analysis. Okay, one other important idea and then we are done. So we talked about the early effect, right? And I want to finish off just with this slide where I provide a little more detail on the early effect. Early is the name of a scientist, okay? It's not early or late in the day, it's just a name. And this slide helps you gain a little more knowledge which may be useful at some point in the future. I am not going to have any problems, etc. related to this. I just have a small example. The early effect is not too important at this stage, but when we do a lot of amplifier design and we get more and more precise, so that we need, we have very small signals, and it's likely, particularly IC circuits, integrated circuits, and it's very likely that because they are such small values, such low microvolt type signals, that you have to be much more precise, then the early voltages and the early effects start to have an impact. So what is the early effect? Now we always pretend that the collector current is only depending on the base emitter voltage, right? We think nothing else matters. But what was discovered by Early is that the voltage Vx, which is the collector voltage, and something called Va, which is, it has the name early voltage, Va, it's a constant. Well, not constant, but it's generally given by the manufacturer to be in the range of 15 to 150 volts. So you have to bring in this factor to define the collector current. So instead of IC equals Is exponent this, it becomes IC equals Is exponent this multiplied by this factor. Generally this factor is extremely small, can be ignored, but sometimes you cannot ignore it. So for example, here's a reverse calculation. If you are given that an IC is about 1 milliamp and VCE, this voltage, is about 2 volts, what difference would the VBE see. Okay, what is the difference? So in one case it's 760 millivolts, another case 758. So hardly any difference, right? But sometimes it does become important. If this is very low, uh, or you're trying to assess the impact on some very low signals, on the right side, for example, is shown the small signal circuit model. And now what is happening is, in the model you have to introduce a new resistance called RO in parallel with this current source. What is this RO? It's VA, this early voltage, divided by that biasing current IC, which you come derive here. So that ratio then gives you two different magnification or gain factors, one without, one with, and you see that depending on the size of that resistance, it can cause an impact. Okay, so I just wanted to introduce this idea to you that the early effect has some bearing, has some impact on small signal analysis, but we're not going to do too many problems. So the very last slide, and I promise you this is the last minute. Uh, this is from the textbook. He has done a very nice summary of all the concepts that we have studied so far in the small signal, including the early effect. And so he gives you the two pi models, the T models with the early effect, what each one of these is, the transconductance, the Re, the R pi, the relationships between them, and how they are also related to the alpha, the betas. So all this is in one table, and that is the summary table. So keep that handy. It will help you to solve problems. Okay. All right. I'll stop here. The next recording we'll do problems on all this material.